We're going to do another example for sketching graphs. I wanted to do something a little bit more complicated so that we could talk about another aspect of sketching graphs that we didn't get to talk about in the previous example. So once again, let's just dive in with a function. And just like before, I'm going to make my list. So my domain. Well, unlike the previous problem, this function is not valid across all values. In particular, because this is a quotient, I'm looking for values that might make the denominator go to 0. And it looks like if I have x equal to a positive 1 or a negative 1, the entire denominator goes to 0, which is verboten, not good. So for the domain, I'm going to say all x and once we start graphing this, you'll see how this comes into play. When I look at the zeros of the function, I believe we've talked about this in class, a quotient like this goes to 0 only when the numerator goes to 0. So when the numerator goes to 0, well, that's fairly simple. That's just x equals 0. So that's the one place where we expect this function to cross the x-axis. We also, of course, need to talk about critical points, which means I need to take the first derivative of my function, which means, oh joy, we get to use the quotient rule. So, low d high minus high d low over low low, low, times the derivative of high, minus high times the derivative of low, all over my denominator squared. Let's see, we've got an x squared. We're also going to have a minus 2x squared, so that gives me a negative x squared, a minus 1, and I'm going to leave this as is. So there's my first derivative. Let's see, so we're going to look for where the first derivative is equal to 0. So again, I've got a quotient here. A quotient goes to 0 when its numerator goes to 0. And so that gives me, and there's no solution for that. As long as we're talking about real numbers, there's no solution. So I've got no values that make my first derivative go to 0. Bummer. What about values that make this quotient go to does not exist, no value? Well, that happens when my denominator goes to 0. So let's play with that. Took the square root of both sides. That's easy enough. Okay, so those are values where my first derivative does not exist. We can, once again, play the little number line game. This is for my first derivative. So these are places where I've got critical points. I want to know what the slope does on either side of that. So let's pick a value like negative 2. I'm looking at my first derivative. Let's see, negative 2 squared is a positive. That's a negative, and I get a square term, so the denominator is always positive. It looks like I've got a negative value over here. Between these two, I've got 0, so that gives me a negative 1 on top. So interesting. Negative here as well. We've gotten used to these alternating around my critical points, but clearly that doesn't always happen. Let's pick a value further out like 2, so there's 2 squared, negative, negative. This is also going to be negative. Interesting. This is shaping up to be a fun little function. Okay, I'm going to tidy up my first derivative just a little bit in preparation for doing my second derivative. I'm just going to square out the bottom. Okay, quotient rule again. Low. Times the derivative of the top minus the top times the derivative of the bottom. All over my denominator squared. Oh, good grief. How does this clean up? Well, I can distribute this minus 2x all the way through here. And I can FOIL these two together. This negative sign will pass through both negatives here, turning everything positive, kind of like that. So let's see, these two terms give me 4x to the 5th. These two terms give me a minus 4x cubed. These two terms give me a positive 4x cubed. And these two terms minus 4x. Little bit of cleanup. I can collect those together. That's combining that term and that term. There. Okay, there's my second derivative. Values that make the second derivative go to 0. That's when my numerator goes to 0. So let's see. Right away, I can factor out a 2x. And I think this will factor further. And let's see, we'll get no solutions out of this one. So we're going to get x equals 0. And from here, x equals plus and minus 1. We can also look at values that make the denominator does not exist. Now I've written this as this squared. It's also this thing to the 4th power. So once again, my inflection points are the only values that make this go to 0 are again plus and minus 1, which we've already got represented. If we do the number line, 0, plus 1, minus 1, and I check values on each side of those. If I plug a negative 2 into my second derivative, I get a negative, positive 12. This is all going to be negative. If I pick a value between negative 1 and 0, like a negative 1/2, that's negative, I'll end up with a positive value here. If I try a positive 1/2, Very small, very small. This will end up being negative, and then I pick another value like 2, and I'll get positive, positive. Yeah, this will end up being positive. So this time we get the alternating sequence that we sort of expect. Okay, let's talk about how to tie all this information together. So my domain, I've got, this function covers all x values except positive 1 and negative 1. So there are places on the x-axis where this function will never cross. Will never cross those values. So let's sketch those in. I'm claiming that's positive 1. That's negative 1. I know the only place where my function crosses the x-axis is right here. And I know my first derivative tells me I've got negative slopes everywhere. Well, if I cross right here and I've got a negative slope, I must have a negative slope here and a negative slope there. My second derivative tells me around 0. I'm concave up on this side, concave down on this side. Okay, that sort of makes sense. Pretty this up just a little bit. What goes on the other side of negative 1 and positive 1? Well, I know I've got a positive second derivative, so I'm concave up. I don't cross the axis, and my slope is negative. So negative slope, concave up, and I never cross the axis. To me, that translates into something like this. Let's try the same sort of logic over here. I know past negative 1, I have a negative second derivative, so I'm concave down with a negative slope. I never cross this line, I never cross this line. So we've got a function that does something like that. And that's this function taken apart, sketched.